This is going to be looking at bond polarity. So we're looking at covalent bonds. And remember that with covalent bonds, the electron pairs are attracted to both nuclei because the Z effective is high for both. They're both nonmetals. So if the Z effective of both atoms are the same, the electrons will be most likely localized about halfway between the nuclei. And when we say localized, so if I have my two nuclei and they are strong, the two pairs of electrons are going to find the highest force of attraction between the two nuclei. So not here, but right smack in between these two nuclei. It's going to be that sweet spot. So remember that force attractive, you're trying to maximize the force attractive, and so that means making the distance between your two negative electrons right here and your two nuclei as small as possible. So if these are two equally strong nuclei, those electrons will be found equally between these two nuclei. So they're going to bounce around a lot, but they'll be localized, they'll be confined to this area right here. We call that bond a nonpolar bond. The electrons are equally bouncing between the two nuclei, and so there's not going to be an imbalance. However, if the Z effective are unequal, then it makes sense that the electrons, the shared pair of electrons, will tend to find themselves closer, more closely attracted to the stronger Z effective nucleus, right? Stronger force of attraction, it's going to attract the electrons that they share more to itself. Remember that the electrons are bouncing forth back and forth, but will tend to gravitate toward the stronger nucleus. And as a result, we call this bond a polar bond. So, equal strength. What are nuclei with equal strength? Well, identical electrons, duh. If they're identical, like hydrogen to hydrogen, neither of the hydrogens is stronger than the others, and so when they share electrons in this bond, this shared pair of electrons will bounce back and forth freely between these two nuclei. So when we're thinking about our Brinkelhoff elements, right, Cl2, F2, all of those, they will have nonpolar bonds. Carbon and hydrogen. So remember that whenever we're thinking about bonding, hydrogen is mentally placed in the same column, in fact, in the same box as carbon. For all intents and purposes, carbon and hydrogen have the same strength of Z effective. And so a carbon-hydrogen bond as well, those shared pair of electrons will bounce back and forth freely between those two nuclei. So the number of nonpolar bonds that can be created is fairly limited because you don't have as many molecules in which they are just of identical atoms or just C and H. Most of the other nonmetal combinations will be an unequal sharing, and we use the periodic table to determine Z effective. All right, so if I'm looking at a carbon-fluorine bond, this is just one bond within the entire molecule. Carbon and fluorine have the same distance and same shielding, but fluorine has more protons. In fact, remember that the three strongest nuclei of atoms that form any sort of interaction are nitrogen, then oxygen is stronger, and fluorine is the absolute strongest. So fluorine has the strongest nucleus of any element that reacts. So in a carbon-fluorine bond, fluorine is stronger, and we show this two ways. In the bond, we draw a little hash and then an arrow in the direction that the electrons are going to be more attracted to. So this shared pair of electrons will bounce around, but will tend to spend more time toward fluorine side than toward carbon side. As a result, fluorine's not totally grabbing the electron away and becoming totally negatively charged, right? I'm not forming an ion. But it does have a slight negative charge to it, a partial charge. Because remember, electrons are negatively charged, so if I'm bringing electrons closer, I'm bringing that negativeness closer to that. So this fluorine becomes more negatively charged, this carbon becomes more positively charged. And we show this with this lowercase delta. So a lowercase delta positive means that this end of the bond has a partial positive charge, and a lowercase delta negative means that this part of the bond has a partially negative charge. doesn't tell us the magnitude of the charge. It just tells us that it's a partial charge. So again, when we're talking about a polar bond, we show it with the arrow pointing in the direction that the electrons tend to be attracted toward, and we also show the lowercase delta with the positive and negative to show the partial charges. So it should make sense that the higher the difference in Z effective, the more polar the bond. In fact, you can think of ionic bonds as incredibly polar bonds, because in that case, the Z effective difference is so high that rather than just sharing it unequally, one completely rips the electron away from the other and the other one loses it. So in a spectrum, polar I'm sharing equally, nonpolar if I'm pulling on this periodic table, nonpolar I'm pulling it more toward one side, and ionic I'm pulling it away completely. So another thing to remember is that the most unequal sharing that we can have before becoming ionic is hydrogen bonded to N, hydrogen bonded to O, and hydrogen bonded to F. So HN bond, an HO bond, and an HF bond in this order. So HN is unequal but less than HO, which is less than the most unequal sharing, which is HF. So HF has the most polar bond. And that's for two reasons. Remember that nitrogen, oxygen, and fluorine have the strongest Z effective of atoms that form bonds. So they are going to be pulling most strongly on any shared pair of electrons. And hydrogen is unique because hydrogen has no shielding. Right? So even though it has the same Z effective as carbon, more or less, when it forms that bond with nitrogen, oxygen, and fluorine, unlike carbon, carbon has the shielding of helium, hydrogen has no shielding. So when as one electron is being pulled toward one side, it exposes on the other side what we call the bare naked proton, an unshielded proton. And it's hard to get more partially positive than an unshielded proton. It's kind of like the difference between a light bulb that has a lampshade that's pulled closer to one side versus a light bulb that has no lampshade whatsoever. That light bulb that has no lampshade whatsoever is going to burn much more brightly, and so it's going to expose that naked light bulb a lot more.